In this next unit, we're going to start to take a closer look at one of these fundamental functions that is carried out by every single thing that's alive, one of those basic things that every living thing does, and that is metabolism. So this is the transformation of energy from one form into another. And to begin to understand this, we're going to go back and pick up some more concepts from general chemistry and then apply those to the biological metabolic pathways. We can basically think of living cells as these miniature chemical factories where all of these reactions are going on all the time. And a lot of these reactions involve the transformation of energy from the energy stored in sugars and other carbohydrates. And this is the process of cellular respiration. Cells are going to use this energy to perform some kind of work, to make something happen. Some of this energy even ends up being converted to things like heat and also light. Bioluminescence is basically excess energy that's being released when these biological chemical reactions occur. Let's start out with just what is metabolism? What are we talking about when we use the word metabolism? So we use metabolism to refer to all of the chemical reactions that occur in an organism. That's pretty broad, right? So metabolism is an emergent property of life that arises from interactions between molecules in very specific processes and very specific orders to make the things happen that cells need to be alive. A metabolic pathway is one of these orderly interactions. So it begins with a specific molecule, goes through a series of intermediates, and ends up with some kind of product. We call this a metabolic pathway. And each step in a metabolic pathway is going to be catalyzed by a very specific enzyme. So again, this is a very orderly process, stepwise, of getting from a starting molecule through a series of intermediates and then finally to a product. So let's just review the different forms of energy. So remember that energy is the capacity to cause some kind of change in the world. And there are different forms of energy, some of which can perform some sort of useful work. As a review, kinetic energy is energy associated with directional motion. Thermal energy is the kinetic energy associated with random movement of atoms or molecules. And remember that when we say heat, we're talking about the transfer of thermal energy from one object to another. And then we've talked a lot about potential energy, energy that matter possesses because of its location or structure. And so there were different forms of potential energy. We've looked at gravitational potential energy. Things like springs store what we call elastic potential energy. But the one that we're going to be most interested in here is chemical potential energy. So chemical energy is potential energy available for release in a chemical reaction. And energy can be converted from one form to another. This is the example we've seen a few times already. So here we've got a ball coming along a river. It's got some kinetic energy due to being carried along by the current. It's got a bunch of potential energy from being at the top of this waterfall. And so this potential energy is going to be converted into even more kinetic energy. So this is going to accelerate as it goes down the waterfall and get even more kinetic energy than it had when it was up here coming along the current. And then eventually it reaches the bottom, and that kinetic energy can be converted into lots of different forms of energy. It can create some sound energy as it hits the bottom. Some of that energy is going to be released as heat. There's going to be some impact energy, so it might deform this ball a little bit when it hits the bottom. That's mechanical energy that's going to be used to deform the object and maybe change its direction to start going in the forward direction instead of in the down direction. So now let's think about the laws that guide this transformation of energy. So thermodynamics is the field that studies energy transformations. And we can say in an isolated system, such as that approximated by liquid in a thermos, an isolated system is unable to exchange energy or matter with its surroundings. So it's fully contained, it's not going to exchange any matter or energy. In an open system, energy and matter can be transferred between the system and its surroundings. And clearly organisms are open systems, and even ecosystems are open systems because they have a constant influx of energy from the sun. They're going to be releasing radiant heat out into space, and so we can say that the Earth itself is an open system. So according to the first law of thermodynamics, the energy of the universe is constant. So energy can be transferred from one body of matter to another. It can be transformed from one form of energy to another, but it cannot be created or destroyed. The first law is also called the principle of conservation of energy. So during energy transfer or transformation, some of the energy is unusable and is often lost as heat. So ultimately, this excess heat that's generated by all of these transformations of energy is going to be radiated away from the Earth out into space, and then that energy is going to be replaced by the more ordered energy coming from the sun. And so that brings us to the second law of thermodynamics. Every energy transfer or transformation increases the entropy of the universe. So entropy is a measure of molecular disorder or randomness. We've already discussed this quite a bit, and this is going to really come into play in this particular discussion. So here's a little illustration of these first two laws of thermodynamics. So this is the conversion of chemical energy in food to the mechanical energy of doing muscular work, and all of the business that the cells do, so transformation of energy from one form to another, energy being neither created nor destroyed in the process, and then that chemical energy is going to be converted to kinetic energy, mechanical energy. Some of it is going to be lost as heat, and so this organized chemical energy with very low entropy is going to be converted into more disorganized forms of energy, such as kinetic energy, and heat is the most disorganized form of energy. It can't be readily transformed into any other form of energy. And then the very highly organized low entropy molecules in these complex macromolecules in the food are being converted to the more disorganized, simpler molecules, carbon dioxide and water. So second law of thermodynamics, increasing entropy. So what do we mean when we talk about the potential energy in chemical bonds? Where does that potential energy come from? So the amount of chemical energy in a covalent bond is based on both the position of the shared electrons that they're sharing in that covalent bond and the distance of those electrons from the positive charges in the nuclei. So the potential energy of a molecule depends on the configuration and position of its shared electrons. Weaker bonds with equally shared electrons have high potential energy. So they're going to store a lot of energy in those weaker, less polar bonds. They're going to contain a high amount of potential energy. And we saw this when we compared the amount of energy that can be stored in hydrocarbon chains to molecules with more polar bonds contained in them. Stronger bonds are going to be ones with unequally shared electrons, so in other words, polar bonds, and those are going to have relatively low potential energy. So remember, these reactions are going to go from high potential energy to low potential energy. So a few examples, something like a carbon-hydrogen bond, those electrons are going to be equally shared, which means they're nonpolar, and these are going to be relatively long bonds, which means that the atoms are going to have a greater distance between their nuclei, and these bonds are going to be fairly weak. It's going to be fairly easy to pull one of those hydrogens off. And then sort of in the middle here, we've got a moderately polar bond between nitrogen and hydrogen, where the electrons are held a little bit closer to the nitrogen. And then having the least amount of potential energy are these short bonds that are highly polar, for example, between oxygen and hydrogen, where the oxygen is holding those electrons very, very close to it, which is going to pull hydrogen closer into a very short bond, and then these are going to have a relatively low amount of potential energy. So in chemical reactions, if products have shorter, stronger covalent bonds than the reactants, then the potential energy in the bonds decreases. So this is going to be something like falling down a waterfall. You're converting potential energy into some other kind of energy, and that will tend to happen spontaneously. The difference in potential energy between the reactants and the products is going to be transformed. In this case, rather than into kinetic energy like falling down a waterfall, it's going to be transformed either into thermal energy or light generally. What makes a chemical reaction spontaneous? It'll be spontaneous if they proceed without any continuous external influence, so no input of energy is required for spontaneous reactions to occur. If the right chemicals are in the right place and the right concentrations at the right temperature, that chemical reaction is just going to occur without any additional energy input. So how do you know if a chemical reaction is going to be spontaneous? Spontaneity of a reaction is determined by two factors. One is what we just talked about, the entropy increases. So if the products are less ordered than the reactants, then entropy increases. That reaction is going to tend to be spontaneous. Number two, if the products have lower potential energy than the reactants, so the shared electrons are held more tightly in the reactants, then that is going to tend to be a reaction that is spontaneous. So in just kind of eyeballing a reaction, if you want to get an idea whether it's going to proceed spontaneously by looking at the chemical equation, look to see if there are nonpolar bonds in the reactants, more polar bonds in the products, larger, more complex molecules in the reactants, smaller, less complex molecules in the products. Chances are that chemical reaction is going to occur spontaneously. The fact that a reaction doesn't occur spontaneously doesn't mean that it's not going to occur. So life is famous for creating lots of order and structure. So organisms create ordered structures from less organized forms of energy and matter. And they do this by the input of energy, by the transformation of energy, by these metabolic processes that we're going to be talking about. So the evolution of more complex organisms does not violate the second law of thermodynamics. Remember, in an open system, we're talking about both a system and its surroundings. And so as long as there is a net increase in entropy in the entire universe, so the system and its surroundings, as long as total entropy increases, the entropy in a particular system can decrease. So order can be created from disorder, but it requires an input of energy. Going back to the first example of entropy I gave you, if you don't clean up your room for a really long time, it becomes disorganized, but you can always expend energy and go and straighten up your room and create order from disorder. So in what sense did the amount of disorder in the universe increase? Well, you used a bunch of muscular effort, which used up organized forms of chemical energy in your body, released them as heat and as kinetic energy, which is more disordered, and that's where the increase in disorder came from your action of creating more order. So similar kind of thing in these biological reactions that are non-spontaneous and actually decrease the entropy in the system. And this leads us to the different kinds of metabolic pathways that we see. So catabolic pathways release energy by breaking down complex molecules into simpler compounds. So this is going to be an example of a kind of reaction that's going to be spontaneous, that's going to increase the disorder and decrease the potential energy in these molecules. Cellular respiration, the breakdown of glucose in the presence of oxygen, is a prime example of one of these catabolic metabolic pathways. Anabolic pathways consume energy to build complex molecules from simpler ones. And so this is the example of cleaning up your bedroom, right? Using energy, creating something more orderly and more complex. So for example, the synthesis of proteins from amino acids is an anabolic pathway. Any of the synthesis of these large macromolecules, the polymerization of carbohydrates, the polymerization of nucleic acids, these are all anabolic pathways. And the name for the study of how energy flows through living organisms is bioenergetics. If we want to know which reactions are going to occur spontaneously and which are going to require an input of energy, if we want to know which reactions are going to release energy and which reactions are going to consume energy, we have a way of quantifying this in terms of what we call the free energy change in the reaction. So to be able to do this, we need to be able to determine how the energy and entropy changes over the course of this chemical reaction. For our purposes, we're not going to actually quantify this, but we're going to give you the equations that guide it so that you can make a qualitative determination of whether energy is increasing or decreasing, entropy is increasing or decreasing, to be able to understand this idea of the free energy change. So the free energy change, the symbol that we use is a delta G. So the Greek letter delta expresses a change from before something happens to after something happens, and that is general through the sciences. So delta G is the symbol for the change in free energy. So G is a symbol that just indicates free energy. So a living system's free energy is energy that can do work when temperature and pressure are uniform, as in a living cell. The change in free energy during a process is related to the change in enthalpy. What is enthalpy? It's a change in the total energy, taking into account all of the different forms of energy involved. And we symbolize that by delta H, that's the change in enthalpy. And it's going to depend on the change in entropy, and we're going to use the symbol delta S to denote the change in entropy. And then it's also going to depend on temperature. So the expression for the free energy change is delta G. The change in free energy is going to equal the change in enthalpy, the total energy change. So energy after minus energy before, minus the product of the temperature times the change in entropy. So entropy after minus entropy before gives you the change in entropy. So this tells us something. The sign of this delta G is going to tell us whether a particular reaction is going to be spontaneous, if it's going to be energy releasing, or if it's going to be energy consuming. So let's just break this down a little bit. So the change in entropy, remember, if a reaction is spontaneous, it increases in entropy. If you subtract the entropy after from the entropy before, if it's a spontaneous process, that quantity is going to be positive, right? Because it's going to have greater entropy afterwards than it has before. So subtracting that from the total, if it's spontaneous, it's going to make this whole term smaller, okay? So if it's gaining entropy, this term is going to be positive. You're going to be subtracting a positive number from the total change in enthalpy, the total change in energy, and this will tend to make delta G smaller. Now, if we look at the change in energy, a spontaneous process has a lower energy state after than it had before. So that means that delta H in a spontaneous process will be negative. So in a spontaneous process, you'll have negative delta H, and you'll subtract from it a positive delta S multiplied by a correction for the temperature. You're going to get a negative delta G. The opposite of this, a non-spontaneous process, is going to decrease the entropy. So this is going to be a negative number that you're going to be subtracting. So you're actually going to be adding the absolute value of this. And then the total energy is going to increase instead of decrease. And so your delta H is going to be positive. So you're adding something to a positive number, and delta G will be positive. So delta G is negative for all spontaneous processes. Processes with zero or positive delta G are never spontaneous. They always require an input of energy to make those reactions go. So spontaneous processes can be harnessed to perform work. Rather than just giving off all that energy as heat or as light, they can actually be harnessed to do something. It's also helpful to think of these changes in free energy as being a measure of the system's instability, so its tendency to change to a more stable state. So one way you can think of this as something that's sitting very close to the edge of a shelf up above the ground. A small disruption of that object is going to cause it to have a big change in potential energy, right? It's going to fall off the shelf and convert that potential energy to kinetic energy. But once it's lost that potential energy, once it's on the floor, you can disrupt it all you want. You can poke it, you can nudge it. It's not going to lose any more potential energy. It's found a stable state. It's not going to have a tendency any longer to try to change to a more stable state. So during a spontaneous change, free energy decreases and the stability of a system increases. And we call this approaching equilibrium. So equilibrium is that state of maximum stability. There's not going to be any further net change in the system. And every time we've talked about equilibrium, we've talked about processes still proceeding, but in a way that causes no net change in the overall system. So this is a state of maximum stability. So a process is spontaneous and can perform work only when it's moving toward equilibrium, not when it's reached equilibrium, because it's not going to change any further. Once it's reached equilibrium, it's lost its capacity to do work. Delta G less than 0 is a spontaneous reaction, and we call these reactions exergonic. So that means that the reaction releases energy. It's an exergonic reaction. And reactions with delta G greater than 0 is a non-spontaneous reaction that requires energy. So it's going to be energy absorbing in order for that reaction to occur. And we call these reactions endergonic. The reaction absorbs energy. So exergonic reactions are going to tend to bring your system to a more stable state. Endergonic reactions are going to tend to bring your system to a less stable state by the input of energy. And if delta G equals 0, that's a reaction that's at equilibrium. So it's at its maximally stable state. So looking at this in a more visual form, so if we think about the free energy and the reactants, if the free energy in the reactants is high and the free energy in the products is low, then you're going to have an energy releasing reaction, and the amount of energy that's released is going to be equal to the difference in total free energy between the reactants and the products. Conversely, in an endergonic reaction, you're going to have low free energy in the reactants and relatively high free energy in the products, and the amount of energy it's going to take to make that reaction proceed is going to be equal in the difference in energy between the reactants and the products. So for spontaneous reactions, they don't necessarily always proceed at the same rate. So they're going to happen eventually without any input of energy, but sometimes they can be very, very slow. So for most reactions to proceed, one or more chemical bonds have to break and others have to form. This is how we defined a chemical reaction way back in week 1 of the class. So how do they do this? How do they break those bonds and reform other bonds? They basically hit each other. So these molecules must collide in a specific orientation that's going to disrupt those bonds and bring the electrons involved nearer to each other to be able to reorganize these covalent bonds. So what's going to cause them to be more likely to collide and collide with more energy? So higher concentrations are going to make it more likely for these things to bump into each other, and higher temperatures are going to increase the number and the kinetic energy of these collisions. Chemical reactions in general will go faster with higher concentrations of the reactants and also at higher temperature. So just to summarize all of these energy changes and how they affect the stability and equilibrium or disequilibrium of the system, here's a good summary from your book. So in all these cases, we've got a high level of free energy, high level of instability, so these are unstable, less stable systems, and a greater capacity to do work. So if you have potential energy due to your height above the Earth's surface, molecules that are clustered all together in a high concentration are going to have high potential energy, And large, complicated molecules are going to have a lot of potential energy involved in those chemical bonds. Some sort of spontaneous change will happen. The free energy of the system is going to decrease. The system is going to become more stable, and the released free energy can be harnessed to do some kind of work. So when this diver jumps off of the platform, he's going to be stable. When he reaches the Earth's surface, gravity is not going to be causing that change between potential and kinetic energy any longer. When diffusion happens, it's going to reach an equilibrium where molecules are equally likely to move into an area versus out of it. So this is when we have an equal concentration of the molecules throughout the volume. And then these more stable, less complex molecules like water and carbon dioxide, they're going to have shorter bonds and less equally shared electrons, and are going to store less potential energy. So how does this idea of equilibrium relate to metabolism? So we can think of this using an analogy of a hydroelectric system where this water is going to have potential energy. It's going to be transformed into kinetic energy, which is going to be transferred to this rotating mechanism that's going to generate energy and make this light come on. So the gravitational potential energy to kinetic energy, transfer of kinetic energy to a water wheel, and then coming to rest in this other chamber. So in a closed system such as we see here, there's no way for water to get in or out, and there's going to be no exchange of energy between the system and its environment. Eventually the system is going to reach equilibrium, right? The potential energy of the water is going to be equal on either side. There's going to be no more transformation of potential energy to kinetic energy. Nothing to turn this wheel and nothing to light the light. So we'll get a little bit of work for a little while, and then it'll reach equilibrium. So life can almost be defined by avoidance of equilibrium conditions. Cells are never at equilibrium. They have many, many mechanisms for making sure that equilibrium is never reached. So they're open systems experiencing a constant flow both in and out of materials. So if we think of this hydroelectric system again in an open system, so now we have water entering the system constantly, being released from the bottom constantly. This constant flow of water is going to keep this wheel turning indefinitely and keep this light on. So this is kind of the trick that cells do to make sure they don't reach equilibrium and make sure that these reactions can keep happening, this conversion of potential energy to useful energy, to work energy. And so this is, as I said, pretty much a defining feature of life. Metabolism is never at equilibrium. We always have a constant inflow of reactants. Those products are being constantly removed and used up, and so the chemical reactions never reach an equilibrium. And in these catabolic pathways where you have a sequence of different reactions, starting with reactants going through a series of intermediates to a product, we can actually release that energy in small steps to be able to gain some kind of work or store some kind of energy at each step. So in the case of our hydroelectric system, if we have, instead of one big drop of the water, a bunch of smaller ones that are going to turn this maybe not as fast, but enough to give just enough energy, electricity to this light, and then another step that again is smaller but turns this enough to power this light. Now instead of powering just one light perpetually, now we've powered 3 lights and we're able to gain more work from the system by breaking up this one big step into several smaller steps. This is the trick that living cells do with these metabolic pathways, and this will become much clearer as we go through the details when we study cellular respiration. So one of the ways that this potential energy is harnessed and stored to be able to do actual work is through using ATP as an intermediate kind of storage for that potential energy. So ATP is going to power the cellular work by coupling exergonic reactions to endergonic reactions. So what is the kind of work that a cell is going to do? So just 3 main kinds of work. One is chemical work, so pushing endergonic reactions being able to synthesize large, complex biomolecules. Transport work, so pumping substances against the direction of spontaneous movement, such as against a concentration gradient. And mechanical work, such as the contraction of muscle cells and the use of these motor proteins to change conformation, to create forces that push and pull against things. So to do this work, the cells manage energy resources by energy coupling, the use of an exergonic process to drive an endergonic one. So if we think of this exergonic reaction, that's going to have high energy reactants that lead to low energy products. That's going to release energy in that process. And so when you have your lower energy reactants, if they can grab that energy somehow and use it, that energy can provide what's needed to be able to increase the energy of those products and have this endergonic reaction. But this is actually not as simple a trick as it looks like. You can't just grab energy from the environment. For example, if this were releasing energy in the form of heat, it would not be able to be used for these reactions. We need to make sure that we've got that energy in an organized way that can be used to do this work of powering these endergonic reactions. And that's where ATP comes in. So most of this energy coupling in cells is mediated by ATP to make sure that this energy is not just wasted as heat or light, but is actually harnessed and captured to be used. And it does this through the transfer of phosphate groups. So adenosine triphosphate is the energy currency for cells. This is basically what's used to do all of those different kinds of work we talked about that cells do. ATP is composed of ribose, so this is very similar to the nitrogenous bases that we saw in nucleic acids. So we've got a ribose, as in ribonucleic acids, attached to an adenine nitrogenous base. So far this is very much like our nucleic acids, but instead of being connected to one phosphate group that's going to link it to other nucleotides, it's connected to a series of 3 phosphate groups. So in these phosphate groups, each of them have 2 negative charges, which are going to repel each other. That force is going to be less strong than these covalent bonds between oxygen and phosphorus, but they are still going to represent a lot of potential energy. So the repulsion means that the phosphate group has high potential energy and is going to be fairly unstable. So how do we get this energy? Basically by hydrolyzing that ATP. So hydrolysis of the bond. This is the same kind of hydrolysis reaction that we saw when we were breaking up polymers, when we were talking about macromolecules, where a water molecule is brought in to break that bond between the 2 outermost phosphate groups. So it's going to lose its 3rd phosphate group in the line, and that's going to form ADP and inorganic phosphate. So this is going to be a highly exergonic reaction. It's going to release 7.3 kilocalories of energy per mole of ATP. So this release of energy comes from the chemical change to a state of lower free energy, not from the phosphate bonds themselves. This is from going from a higher energy state to a lower energy state. And here is just a visual of what we just talked about. So here's our adenosine triphosphate ATP with a ribose sugar, an adenine nitrogenous base, and then our 3 phosphate groups, which is going to combine with water in a hydrolysis reaction. 1 hydrogen is going to be added to the last phosphate group. The other hydrogen and the oxygen are going to be added to the inorganic phosphate, and then 7.3 kilocalories per mole of ATP of energy is released. So still, if this is all we're doing, if we're just hydrolyzing ATP, that energy is still being wasted as heat or possibly light. So how do we actually harness that energy? How do we keep it? How do we keep it from just becoming totally disorganized and lost? We do this by, instead of just releasing that inorganic phosphate out into the world, we're going to transfer that phosphate to another molecule to give it higher energy and to make it more unstable. So the energy released during ATP hydrolysis is transferred to a substrate by phosphorylation, the addition of a phosphate group to another molecule. So this is going to usually cause a change in the protein's shape that's going to give it a higher energy state than it had before. It's going to make that protein less stable. So then, exergonic phosphorylation reactions are coupled to endergonic reaction. Okay, so let's see how this is coupled together. So first let's look at the uncoupled reaction. Your two reactants A and B are combining to make AB. So normally if we're not going to use ATP, these reactants are at a lower free energy state than the products. So we need an input of energy of delta G, the difference between the free energy of the products and the reactants, to be able to make this go. So here is the energy state of the final product AB compared to the energy state of the two. If you add ATP in as a reactant, now the combination of all of these reactants have an energy state 7.3 kilocalories per mole of ATP, and that phosphate is going to be added on to B. B is going to be phosphorylated, ATP is going to be hydrolyzed, that's going to release energy. But it's not going to release the full 7.3 because this phosphate hasn't just been released into the environment, it's been added to B. So we're still at a higher energy state of these reactants than the final energy state of the products, because this phosphorylated version of B has much higher energy than B does by itself. It's less stable. And so in this first reaction, we've got A plus phosphorylated B plus an ADP, which is then going to go through another exergonic reaction, because remember B is now unstable. That's going to bring it down to its final energy state, which is lower than either. So now we've taken this in steps, and we've been able to use the energy in that ATP phosphate bond to actually drive an endergonic reaction. Another example, more relevant to biology, is this reaction of combining glutamic acid with ammonia to create glutamine. So this is an endergonic reaction that costs 3.4 kilocalories per mole, but when we instead use ATP as a reactant and phosphorylate that glutamic acid and generate phosphorylated glutamic acid plus ADP as the products, now that phosphorylated glutamic acid is less stable, it's going to react spontaneously with ammonia in an exergonic reaction into that glutamine product plus ADP plus the phosphate, which is then going to be released in the process of this reaction. So the total reaction, so just this part of it, costs 3.4 kilocalories per mole. The hydrolysis of ATP, the total thing, first hydrolyzing the ATP and phosphorylating the glutamic acid, and then the final release of the inorganic phosphate is going to release 7.3 kilocalories per mole. So we've got a net loss of free energy of 3.9 kilocalories per mole, which will be given off as heat. So similar to ATP being used to drive these chemical reactions, these endergonic chemical reactions, ATP is also used in a similar kind of way for the other kinds of work that cells do. So transport proteins are going to involve the phosphorylation of that transport protein. This is exactly what we saw in the sodium-potassium pump, with the pump protein being phosphorylated. That phosphorylation is going to cause a change in shape. When that phosphate is released, it's going to change back to its original shape, and that's going to allow the transport of these solutes. Similarly, with a motor protein, the phosphorylation of ATP is going to cause a shape change in that motor protein, which is going to make it move, change shape, and find the next binding site down this microtubule protein polymer and move step by step along that cytoskeletal track. And so we've taken an ATP, we've phosphorylated something, and we've ended up with ADP and an inorganic phosphate. Now what happens to that ADP? Where does it go? Well, it turns out that ATP is a renewable resource that's going to be generated by the addition of a phosphate group to adenosine diphosphate. So it's going to take those two products and put them back together. And the energy to phosphorylate ADP back into ATP is going to come from the catabolic reactions in the cell. So basically cellular respiration, which we will get to in another couple of class sessions. So The ATP cycle is like a revolving door through which energy passes during its transfer from catabolic to anabolic pathways. So if we think about, here is our used up ADP and phosphate that we got from that endergonic reaction coupling. So it's at a low energy state. We're going to get an energy input from the catabolic processes of breaking down large macromolecules in an exergonic energy releasing process to create this more complicated, less stable, higher energy ATP plus water. Okay, so this is similar to those polymerization reactions, the dehydration, also known as condensation reactions. So water is going to come out just as a water had to go in to do this reaction. And then those are then going to be used as energy for endergonic, energy-consuming processes, converting them back into ADP and inorganic phosphate. So to wrap up, let's just review how all of this fits into the idea of metabolism. So again, metabolism is the totality of an organism's chemical reactions. All of these pathways, all of the work that cells do are part of this idea of metabolism. So metabolism is an emergent property that comes from these pathways, this orderly progression of reactants, intermediates, products that are going to couple these exergonic with endergonic reactions to create more order in the system of the organism. As we said, a metabolic pathway begins with a specific molecule, and it's going to proceed through intermediates. If this is an catabolic reaction, these are all going to be little exergonic reactions from one intermediate to the next, sort of like those little steps we saw in the hydroelectric system. If this is an anabolic pathway, each one of these reactions is going to be coupled with an exergonic reaction in the form of phosphorylation of the substrate by hydrolysis of ATP to get to the final, more complicated reaction. And so how these enzymes work to help this happen is going to be the topic of the next segment of this chapter.